All right. Hello, everyone, and welcome to Day 8, Lecture 25. Today, we're going to be talking about A/B testing. And in fact, what I'm going to do is I'm going to tie up basically everything we've done in the course so far and see how it all relates to each other. So let's go do it. Some announcements. So as you guys know, Project 2, the checkpoint, is due tomorrow at midnight. And the actual project is due Tuesday at midnight. Okay, so please make sure you have the checkpoint done tomorrow and the entire project done on Tuesday. Finally, you'll notice that for the lecture for today, the textbook links, you'll notice that the textbook links coming from like a chapter that's way beyond what we're normally doing. That's because I've reordered around the material a little bit for the summer. What we're going to do is we're going to update the textbook to match the summer schedule. However, that hasn't happened yet. So if you go visit the textbook links, you may see that there's some terminology that you're not familiar with. Don't worry about that. But the demo and the code in the textbook should be the same. Okay, cool. So we spent this week talking about comparing samples, right? So if we have two random samples, sample A and sample B, we want to see, is there a difference between the two samples? For example, we looked at Deflategate. So we said, OK, do the two teams' footballs look like they came from the same place? Okay. So oftentimes when we have two random samples, our question is, are they drawn from the same underlying distribution? The way we answer that is with A/B testing, which is basically what we've done so far this week, just with the name attached to it. It's A and B because we have sample A, sample B. Usually our hypothesis for this case is the two samples are drawn from the same underlying distribution. They look like two draws from the same set. So our two teams' footballs, the drops in pressures are drawn from the same place. There's not much difference between the two. Our alternative is that although the samples look different, they are in fact actually different. They came from different places. Okay? So usually when we make hypothesis tests, our null hypothesis is kind of contrived sometimes. So for example, if we have a coin, we may presume that our coin is fair, but in reality, like if you lived in a world where coins land on our heads 70% of the time, then in that case, the null hypothesis would be coins land on heads 70% of the time. So a lot of times, like when we set our null hypothesis to be like, oh, the proportion of this is this, or the probability of that is that, it feels kind of contrived because we're just arbitrarily setting numbers to be equal to something. But in this case, when we're comparing two samples, it makes a lot of sense to set a null hypothesis that's this, which is the difference in means is 0, or the difference in medians is 0, or something like that. It makes a lot of sense to set a null hypothesis of something minus something else equal to 0 when we're comparing two samples. Okay. What we did earlier this week when talking about this kind of A/B test was to use a permutation test. Okay, so that was a method that we used for taking new samples from the population given our original two. Okay, so if our null is that the two samples are drawn randomly from the same distribution, then all rearrangements of our data should be equally likely. So the key idea was, since that's the case, shuffle our data, compute another test statistic, and use that to get a distribution of our test statistic. Okay, so compute, then shuffle, repeat, and then compare with our observed, and compute a p-value as we've done before. Okay. Any questions about that? All right, so let me make a brief aside and talk about the test statistic. So we run into kind of two broad cases when we're comparing two samples. the case that we've seen first in this class was just if the samples are numerical. So if we're looking at the drops in football pressures, we're taking a look at that and we're like, OK, the drops in football pressures are numerical, so we can take the difference in means and just be done with it. That's our test statistic. Sometimes it's not so clear. Like sometimes it's not like one single numerical measure. So for example, we might want to look at, so we are going to look at, let's say, do people who work out have bigger t-shirt sizes, right? So in that case, we'll take people who work out, people who don't work out, and look at their t-shirt size distributions, right? So that's not numerical data. We're saying, oh, this person who worked out wears a small, this person who didn't work out wears a medium, etc. And from there, we want to do, so that's categorical data. So instead of using the difference in means, we use a TVD. But all in all, like choosing a test statistic is pretty much the same as what we've done before. We just look at our data and choose a test statistic that makes sense given our data. OK, cool. So let me do a demo. Full screen. Cool. So what we have here is the same table that I had from yesterday, which was looking at data on newborn babies. Okay. And I mentioned before that this was data, and they were trying to look at whether or not the mother's smoking was related to any aspect of the baby, like the weight or pregnancy weight or all of that stuff. Okay. So the idea here is there a relationship between smoking and weight? Yesterday, we did not look at that. Yesterday, instead, what we did was we used a bootstrap confidence interval to get an estimation for the population weight, the population gestational days, and the ratio between the two. Okay. But today, what we want to look at is there a difference in baby weights for people who smoke versus people who don't? Okay. So let's take a look at that. So write that down. Is there a difference in baby weights? Mothers who smoke, and mothers who don't. Okay. So our null hypothesis in this case is that there's no relationship between smoking and not smoking and your baby's weights. Our alternative is that there is. So let's try to figure out what it is. So we can group by the maternal smoker column just to see how many of those we have. So if we group by that, we see that there were 715 non-smokers and 459 smokers. Let's look at the weights of their babies. Is baby. And take out only the rows where the maternal smoker is true. True. Let's do false first. False, and then histogram that. And we have to select out which column is histogram, otherwise it draws all of them. So let's pick out birth weight. Birth weight. Okay. We have here this distribution. Let me adjust the bins so that they're a little bit nicer. Call that weight bins. We could go from 40 to 180 with increments of 5. Okay. Put that here. Bins equals weight bins. And my unit is ounce. Here we go. Okay, so here is a distribution of baby weights for mothers who didn't smoke. We can look at that and we can see, oh, OK, it looks like most of them fall at around 130, 120 ounces. Okay. Let's look at the ones for mothers who did smoke. So I just need to copy and paste that down here. Change that to true. And there we go. So we have the baby weights for mothers who did smoke. It looks like they're a little bit lower, right? So you compare. I also have a cell here that draws them both on the same histogram. It's a little bit more complicated, so I'm not like typing it in right now, but I'm just going to draw it. Okay, so draw that. And we can see here, OK, so the blue are baby weights for smokers. Yellow are baby weights for non-smokers. So we take a look at that. So talk over with your partner. Just like looking at this histogram, do you feel like there will be a significant difference in the baby weights, in the mean baby weights, if we run a hypothesis test? Go ahead. Just take a guess. OK, how many guys think yes? How many guys think no? OK. How many guys think yes? Let's try this again. How many guys think no? Getting some non-response bias. It looks like most of you guys think yes. And yeah, in this case, I look at this, and although it seems like there's a big overlap in the two distributions, if you say, for example, look at this region over here on the right, for every single bin, then there's like more babies in the non-smoker category as there are in the smoker category. And for this region over here, for every single baby in basically every single bin, for every single bin, there's more babies in the smoker category than there are in the non-smoker category. So this says, OK, there might not be like a huge separation between the two, but it looks like there's some like systematic difference here, right? It's basically always bigger here. So let's see if we can quantify that using a hypothesis test. So we have here a baby table. Show that. We choose as our test statistic the difference in mean weight. Okay, so take the babies who had mothers who smoked, take the ones who didn't smoke, find the mean weight, subtract the two, and take the absolute value, because our alternative is that there is some association, not that it goes in a certain direction. Okay, so there is some association, so we need to take the absolute value. So let's take baby and select out. Call this smoke weight, and just select out the two columns I'm interested in looking at. So select out column number 0, 1, 2, 3, 4, 5. Select out 0 and 5. So here's my smoke weight. And if I take that and group by the first column, or group by the second column, we get that. But I want to do np.mean, so I can take the average weight. Okay, so here, if I group by the maternal smoker column and then average the other column, we get here the average weight. Finally, we can compute that difference. So let's call this means. I want to compute the difference between these two numbers. That's not too hard. Grab that first column, grab item 0, grab the second column, grab the first column, grab item 1, and that is a difference in means. So we're going to be doing this over and over again with different samples. So what I'm going to do is I'm going to put that into a function. Okay, I'm going to call it difference in means. And I'm just going to copy and paste all of that in here. But what I'm going to do is I'm going to say, OK, the function will take in a table, like smoke weight, and it's going to compute the test statistic on that table. So I'm going to replace smoke weight with t, and I'm done. Return. Then I can call difference in means on smoke weight, and I get back the same thing. Okay, so take the code here, put it in the function so I can reuse it. That's all I'm doing. Okay, so here I have this function, and here I have this monster of a function, which I've already written, thankfully, that runs the entire permutation test. Okay, so I'm not going to go through all the steps. If you're curious, you can look through all of this code. Basically, we're doing the same thing as we discussed before. Shuffle the weights, compute another test statistic, shuffle the weights, compute another test statistic. This does it all in one function, so I can just call that function and be done with it. Okay, so let's do that. The way this works is I just call permutation test means. I have to run that. Permutation test means on my baby table. I pass in the variable I'm interested in looking at, and the maternal smoker, the column of the categories. How many repetitions I want, so let's say 1,000, and it's in ounces. The baby weight is in ounces. So I run that, and it broke. How did it break? Birth weight. Birth weight. Okay, let's try that. So it's gonna chug along, simulate a bunch of samples, and there we go. Okay, so that looks a little bit odd. And that is because I forgot to put an absolute value here. Let's try that. Absolute value. Oh, wait. Baby, birth weight, maternal smoker. Puzzling. Strange. Mutation test means. I swear this worked yesterday when I ran it, but it is not working now. Column. Oh, I know what it is. I mixed up the order of the columns here. So group by the 0th column, then grab column 1. Yeah. Okay. Mix up the order. So I should have put 5 and then 0 to match up the code that I already written. My bad. So let me do that. Match it up. Okay, match it up. All right, now we're going to cross our fingers. This is going to chug along. And there we go. OK, so what do you notice about this distribution? Talk over with your partner what we can conclude. OK, so make sure you get your wording as precise as you can get it. So what can we conclude based on this distribution, our observed, our p-value, and our null and alternative hypothesis? Talk it over with your partner.
So I don't think you can see the number like this. It's like the history doesn't go that far. So I guess we have pretty sufficient evidence that there is a really the R&D funding. Don't smoke, right? I'm actually at an age where I can it's legal for me to smoke. I just don't want to. I just would never do that.
All right, so we look at this distribution, and we're like, if my null hypothesis were true and smoking did not affect the weight in any way, then I would expect to see differences of around like 1, of 2, maybe 3 sometimes, but never 9.26 is like really far out, right? And that's reflected in the fact that our p-value is 0, which basically means, OK, like if our null hypothesis were true and smoking had no association with baby weights, we would basically never see our results, which leads us to the conclusion that, OK, we can reject the null, and we think that there is an association between smoking and baby weights. But so that's basically all we can say, right? Based on our null and our alternative and what we've done here, that's all we can't go any further than that. All we can say is that there is some association between the two. We unfortunately don't know in what direction that association is. We unfortunately don't know how big the difference is between the two, right? So our hypothesis test allows us to answer the questions of like, is there an association? Is something more likely to occur, less likely to occur? But sometimes what we're really interested in is the effect size. I'm getting ahead of myself. Let's take attendance first. Oh, it looks like I left it online from yesterday. Oh well. So again, the URL is bit.ly/@-d. There is no more 8 because we changed the link. We changed the link. There's no more 8 at the end. Yes.
So if your p-value is 0, does that mean like you're 100% confident then in that you're not falling?
Yeah, so I'll be careful with the terms like confident because we use confident to describe something else in this class. If our p-value is 0, we basically can say, OK, if our null was true, it looks like what we observed would never happen. So in our actual data, we saw that for babies born to mothers who smoked, that's one group, and for babies who were born to mothers who didn't smoke, that's another group, there's a difference in weights of about like 9 ounces, right? So babies who had mothers who smoked, babies who had mothers who didn't smoke, the difference in weights, difference in average weight was about 9 ounces. And the p-value of 0 says, okay, well, if there was no link between smoking and baby weights, and we did our permutation test, we looked at, so if there's no link, and we looked at what would have happened by random chance, right? So if by random chance, so even if there's no link, by random chance, you can just get some babies in one group and some babies in another group, and the means could be different, right? So by random chance, there could be some differences. It looks like based on our distribution, the difference could be 1 or 2 or 3 ounces maybe. But we got 9 ounces. So that p-value of 0 basically says, OK, that seems like it's really, really, really unlikely to occur if our null hypothesis were true.
It's like 0 chance then.
So it's more like, OK, if our null were true, then there would be almost a 0 chance. So it's important to say that it's if the null were true, there's a 0 chance, because it did happen. So obviously a chance is not 0. Like that particular thing happening is not 0. But if our null were true, then we would not expect to see this very often. That's what it's saying. OK, cool. So we ended by talking about the limitations of the hypothesis test, basically. We can use the hypothesis test to establish association, but we can't really use it to get a sense of our effect size. Fortunately, we have now a tool in our toolbox that can do that. Okay? So if we're asking the question, OK, we know that there's an association, but I want to know how big that difference is and whether or not it's actually smoking or not smoking that makes your babies weigh less, then I want to use, so instead of running a hypothesis test, I just want to say, OK, what do I think that difference is between the mean weights? Okay? So instead of saying, OK, there is a difference between the two distributions, I'm asking a slightly different question, which is, how much can that, so we observed a mean weight of difference of 9. Our question is, how much could that vary? Okay? And we've done something like this before. In fact, we did it yesterday. Instead of doing a hypothesis test, we'll just bootstrap the sample and construct a confidence interval for the difference between population means. That'll give us a way to estimate, OK, in my population, there's probably around like negative 0.3, negative 3 to like negative 12 difference in ounces, or maybe it's the opposite way. We won't really know until we run the confidence interval. But a confidence interval gives us a range of values that we think is possible. And because of that, we get a sense of how big, how the magnitude and the direction of our observed difference. Okay, so let's try it out. So conveniently enough, I have here a function that does the bootstrap confidence interval, so I don't have to do it myself. And all I have to do now is call it. Right. So let's take a confidence interval of the difference between the mean weights. So I'm going to pass in baby, see if I can get this right this time, birth weight. Maternal smoker. Let's do 1,000 repetitions, and the unit is in ounces. Okay. And here we go. So what this is doing is it's taking our sample and constructing a bootstrap confidence interval as we've done yesterday. So we take our samples, we resample, find a difference between means. Okay, that's one trial. Resample again, difference between means, another trial. We plot all those means on this histogram here. And we can see here that we've computed our confidence interval of about 7 ounces to 11 ounces, right? And in this case, what we've done is we've said, OK, this difference here is not the absolute difference. It's instead just for mothers who didn't smoke minus mothers who did smoke, the baby weights there. Okay, so we took mothers who didn't smoke minus the baby weights of mothers who did smoke. It looks like that difference is about 7 ounces to 11 ounces. Right? So we can conclude that chances are we conclude that there's probably about this much difference in the population, right? So it looks like for mothers who did smoke, their babies weighed about 7 to 11 ounces less. Okay? So that's the association that we can see there. So we get not only which ones weighed more, but we also get a range of values that we think are possible. Okay, so very convenient. Cool. So now that we have two functions I can just reuse over and over again, let me just try to look at some different variables. Okay, so here I had a baby table. I wonder if there's an association between maternal smoker and maternal age. Is there an association between smoking and age? Let's find out. Okay, so we first run the permutation. Just going to copy and paste this. All of these are the same. Bam. And instead of looking at birth weight, let's just look at maternal age. Run that. Right. And it's going to chug along. Okay, so we do see that there is an association, right? So we got a p-value of 0.02. It looks like what we observed was that there's a difference of 0.8 in our maternal age. But that results in an empirical p-value of 0.02. Right? So it looks like there is some association between maternal age, between smokers and their age at which you give birth to a baby. All I'm going to do is change that to get a bootstrap confidence interval. So let's change that, and here we go. Bam, confidence interval. Bam, confidence interval. There we go. Okay. So we can see here that it looks like right here the difference in means was about 0.13 to 1.46. So we can take a look at that and then make some conclusions there. Okay, so we get a sense of the range and difference. So we can do a permutation test in one call, bootstrap CI means in another call. We can do all that in just a couple lines of code. Now that I've gone through all the work of talking about how these functions work and what goes into them, we can just use them. Very convenient. Let me do one more. I wonder if there's a difference between the maternal heights. Okay. So your intuition probably says no, hopefully, that there's probably no difference between the heights of people who smoked and didn't. But let's see if that's actually the case. Permutation test means, I'm just going to copy that. Copy that, replace that with permutation test. Replace maternal age with maternal height. And bam. OK, so what do we see? The average difference in heights was like 0.09, which is pretty small. And our p-value was pretty high, so 0.55. This tells us that, OK, we can't conclude that there's an association between smoking and not smoking and the height at which you have your baby. Okay, so it doesn't seem like there's any link between the two. And indeed, we observed that to be true in our hypothesis test. We can also use a bootstrap confidence interval here. And this will tell us basically the same story. So what will happen here is that we'll get a range of values. So we'll say, OK, it looks like what we can expect the difference in heights to be is about about 0.4 less or 0.2 above. But you notice here that 0 is contained in our interval, right? So it's perfectly plausible that there is actually no difference after all, right? Because if 0 appears in an interval, then we can say, OK, in our actual population, it seems like there could be no difference between the heights of mothers who smoked and mothers who didn't smoke. Cool. Any questions? Yeah, Kevin?
So we're basically looking for if the null hypothesis is in the confidence interval or not.
Yeah, so in this case, so what we did in the bootstrap confidence interval is we said, OK, I observed some test statistic. So let's say the difference in heights between mothers who smoked and mothers who didn't was like maybe 0.2. So I think it was 0.2 in our case, or 0.02, right? So we observed something, and we use a bootstrap to say, OK, draw more samples, find out the variability of my test statistic. So we know that even if there was no difference between the two groups, we could still get, so if there was actually no difference between the heights of mothers who smoked and mothers who didn't, we could get some differences just based on chance, right? So the bootstrap confidence interval gives us kind of a sense of how much that varies. So we say, OK, basically this is saying, OK, our observed test statistic was, let's say, 0.02. And the confidence interval says, OK, well, that's close enough to 0 that it looks like there's no relationship between the two variables. Because 0 is contained in our interval, which means that it's pretty likely to occur if our null was true. Any other questions? All right, so this can get pretty nuanced and confusing. So I encourage you to practice some more, run through the notebook, try out like different hypothesis tests on different variables if you'd like, and try to predict beforehand. So this is a really good exercise. Try to predict beforehand whether you think there's a relationship or not. In the real world, you'll have a lot more variables than what I have here. So in this case, the baby's table only had, let's say, like six columns. In real life data, sometimes we get like hundreds of columns, okay? And you have no way of knowing, like, okay, I can't just look through every single one and do a hypothesis test on every single one because, it doesn't seem, would take too long. So instead, you want to be able to kind of look at it and say, okay, I expect there to be a relationship between these two variables, and then try to like cut down the amount of time you spend looking through like hundreds and hundreds of variables. Okay, so try to look through that on your own time. But now I get to go back to the very beginning of the course. So what I'm going to do is turn off attendance. Close the form. OK. And I can take us all the way back to the second lecture of the course. If you'll remember, we talked about John Snow. John Snow was looking at cholera in London. And he was trying to say he thought that the water was causing cholera, right? So what he did, if you recall, is he like went around the town, asked everyone, like, okay, like, did you drink from this pump? How many deaths did you have in this building of cholera? And he plotted them on a map, and he can see, okay, it looks like most of the deaths are clustered around the Broad Street pump. So he said, okay, everyone, let's remove the Broad Street pump handle to keep people from drinking from that water. And lo and behold, people stopped getting sick. People stopped getting cholera after that. But if you remember, all he did with that little experiment there was establish an association, right? So he was not able to say, okay, water caused cholera. He was only able to say, okay, it just so happened that the deaths were clustered around the pump, and it just so happened that when I removed the pumps, people stopped dying. But I didn't account for any other factors that could have stopped people from dying. It could have just been the fact that the cholera was on like the downturn, right? So he was not able to establish causation there. What he had to do, he had to go a step further, right? We had to look at the maps of the two water companies in London. I don't remember the names. I think it was Lambeth and S&V. And he looked at the areas where the two water companies overlapped in service, right? So if you're living in this particular region of London, you can get water service from either Lambeth or S&V. And the critical assumption that we made there, or he made there actually, was to say, okay, if you're living in that area, you're going to pick one of these two companies, and it's going to basically be random which company you pick, right? Only with that critical assumption could we say, okay, the group receiving water from Lambeth and the group receiving water from S&V look mostly the same, because we use random assignment to kind of get rid of or kind of account for those differences between the two groups that could have occurred by chance if it was just like rich people got one group and poor people got another water company, right? So the key to establishing causality is, if we have sample A, which is our control, sample B, which is our treatment, they need to be similar in every way except for our treatment. Only then can we say, okay, sample B, or the treatment, must have caused whatever effect that we're noticing here, right? And the way we do that, the way we account for those differences, is to separate people into those two groups at random, right? So even if we had one group of people that were just really tall and one group of people that were just really short, if we randomly shuffle people into those two groups, so control and treatment groups, then you can say, okay, the two groups look mostly the same, right? Because some tall people will end up here, end up here. If we shuffle, we can account for a lot of differences that we wouldn't be able to otherwise. Okay, so that randomness allows us to say those two groups look mostly the same, which means that any differences in outcomes between the two groups is either because of random chance, we got unlucky, or because of our treatment. Okay, so this is, for statisticians and for most people, one of the only real ways to establish causality. And right now it's considered like the standard for people in medicine, for people in most fields. If you want to establish causality, like my medicine makes people feel better, you need to run an experiment like this with a randomized controlled trial. Okay, so let's go through one example. So I have here, conveniently enough, an example from medicine. So this was an experiment done looking at treatments for back pain. So some people have really chronic back pain, and it causes them a lot of problems. And basically, we've tried a lot of stuff, and a lot of stuff seems to not work. In this case, what they tried was they thought, OK, maybe if we inject the botulism toxin into your spine in small quantities, that will help your back stiffen up and feel better, right? So this was so basically all that details is taken out of this little table here. All we have in this table is, let me see if I can make that bigger. All we have in this table is our control group and whether or not they felt better after the treatment. And if you keep going down, let me show all the rows. We have here the treatment group and whether or not they got better after receiving this treatment. Okay? So we have control, treatment, whether or not they felt better. And let's see if there's a difference between the two. Okay? So this was, most importantly, this was a randomized controlled trial. Okay? So what they did was they separated out participants into two groups. They didn't tell them who got what treatment. So the control groups got a saline solution. The treatment group got the actual toxin. And they also did not have the test administrators know which group was which. Okay, so it's called in medicine a double-blind experiment, where neither the patients nor the people giving them the treatments know who's getting what treatment or what's actually happening. That way, there's less bias involved. Yeah.
You already answered.
Okay. Yeah. Cool. So we have here what we consider a pretty well-constructed randomized controlled trial where people were randomly assigned. Okay, so let's see if we can find a difference between the two. And then we can establish some causality. Here we go, show 3. And let's take a look at, let's group by the control and treatment group column and take the average of my results. So we can see here that on average, in our sample at least, this sample contained maybe 31 people, looks like. So we have 3 rows here, 28 rows left, 31 people. 60% of the people who got the treatment felt better, and only 1/8 of the people who got a control felt better after they got their control. Okay, we'll see the difference is significant. And to do that, I could go through and rerun the entire permutation test thing again, or I can just call my function. Permutation test means look at my results column, the categories are my group column, and let's run 1,000 trials of that. And okay. So what I've done here is a distribution of my test statistic, which is looking at the difference in the means of people of this treatment column or the result column. And what we see here is that we observe a difference of 0.475. So this minus this is 0.475. And our empirical p-value is 0.01. Which would lead us to a conclusion that, yes, there is a difference between the two groups if our p-value cutoff was at what it typically is at 5%. Okay, so we had that. And then we can do the bootstrap confidence interval. Here's a bootstrap confidence interval for a difference. And we can see here that the confidence interval goes from negative 0.75 to negative 1.15. Okay, now this is probably one of the most difficult things to interpret in this entire class. So go ahead and talk with your neighbor. What do you think that confidence interval actually means? So based on this confidence interval, we can conclude that blank. Try it out with your neighbor.
Look at the difference between right? Was even 0 or 1? Else the 500 got the average decimal, the square decimal. So we're taking the difference between the two units. And we do that many times, like that, and plot onto it. So we have the middle 95%. Yeah.
All right, so we have here a confidence interval for the difference between means. But what does that actually, what is the significance of that? So if you look at the table we have up here, we had here a 1 whenever someone got better, and a 0 whenever someone did not feel like they got better from the treatment. Okay. The key to notice here is that if I take the mean, what I'm getting is a proportion of people who felt better, right? Because if I have 100 people and 60 people said they felt better, so 60 of these are 1s, and I have 40 more 0s, if I take the average of those 1s and 0s, I get the proportion of people who felt better, right? So what I have here is 12% of people felt better, and 60% of people felt better for the treatment. So this difference between means is actually a difference between proportions of people who felt better. What we're saying is that in real life, if I looked at the entire population of people with back pain, there is some real proportion of the difference in, so if I look at everyone in the whole world who had back pain and gave some people saline solution, so a placebo, or and gave some other people the actual treatment, if I give people a placebo, there's some proportion of people who would feel better. Okay, so that's one group. And for the people who got the treatment, there's some proportion of people who would feel better for there. So maybe let's say this group, 12% felt better, and for my treatment group, maybe 50% felt better. Okay? In a population, there is some actual parameter, which is a difference between those two proportions. This confidence interval is saying, I think that actual population difference between the two is between 75% and 15%. So as before, we noticed that, OK, it looks like a confidence interval does not include 0. So it looks like there is some difference. In this case, we're doing the treatment group minus the control group. So it looks like people did feel better after the treatment, which is also true based on our data here. So people did feel better after a treatment. And so we can say it looks like about 75% based on our data. We can estimate the population parameter at about 75% better to 15% better. So we look at that and we say, OK, that's a pretty big confidence interval. Right? So we don't really know. We don't really get a good sense of what the actual proportion is. But we can say it's not 0. So there is some benefit to doing this treatment based on our data. Okay. Now, if you wanted to actually make this interval smaller, we have to go ahead and do some more experiments, right? Because the more experiments, the more people we have in our data set. So here we only have 31 people. If we went out and grabbed another 31, our interval will be smaller because there's less variation in our sample statistic as we get a bigger sample size. So as our sample size increases, this distribution right here would shrink and get more towards the middle. And that gives us a more precise confidence interval. But that's not something I can accomplish today because I can't go out and actually give people treatments. Okay. So just to recap, but because that data set came from a randomized controlled trial, what we can conclude is that the treatment caused people to feel better. Okay? So our data suggests that the treatment is actually has a causal effect on how much better, or how much their back pain got better after the treatment. Okay? It's the only way we can establish causality in this class, at least with the methods that we've discussed here. But it's really important because we started out with that question, and then I started you off with that question, and then we kind of got sidetracked with Python, and then we got sidetracked with hypothesis testing, and now we come all the way back, full circle. This is the last lecture on inference that we have for a while, and it's a good place to end off, because now we've finally gone back to the beginning of the class and said, OK, we have all the tools necessary to analyze the data, to do a hypothesis test, to do a confidence interval, and now we know the criteria for establishing causality. And this concludes our lectures on inference. See you tomorrow.